Okay, YouTube, in this video we're going to be looking at binomial expansions as kind of a lead into the binomial theorem. But basically, binomial expansion is what we look at when we get, like a binomial, like you see this x plus 1 here, is a binomial to a power of n that is 0 or greater. And so you can see that at first, evaluating something like this, x plus 1 to the 0, anything to the 0, of course, would be 1 here. That's pretty simple to do. And even something to the first power, we could write this as just x plus 1. And you know what? I'm going to drop the parentheses. I'm just going to write as a matter of fact, I'm going to write 1x plus 1, just to be clear, and then x plus 1 squared. Now remember, we actually have to FOIL something like this out, but this is something that is not beyond us either. That was pretty quick to do there when you FOIL this out. So I'm going to go ahead and write 1x squared plus 2x plus 1. I'm going to put a box around this, put a box around this, and we'll put a box around this right here. So we've got x plus 1, or this binomial here, to the 0, first, and second power. You can see how it's really easy to evaluate. But when you start to get to something like the third, which is x plus 1 times itself 3 times, it starts to get a little bit more cumbersome. So I'm actually going to write this as x plus 1 squared times another x plus 1 to the first, which is x plus 1 to the third. The only reason I mention that is because I've already evaluated x plus 1 squared. So what I'm going to do is I'm going to rewrite this as, I suppose I could use purple here, x squared plus 2x plus 1, and we're going to take that times this other x plus 1 right here. And so already, I really don't like to do this, but we say x squared times x is x to the third power, pardon me, and then x squared times 1 is x squared. And so we'll take now our 2x through, and we get plus 2x squared plus 2x. And then we'd say, bringing our 1 through, we get plus x plus 1. And so let's combine our like terms here. We've got a total of, and in total here, I'll write this underneath here, 1x cubed plus it looks like 3x's squared plus 3 total x's here plus 1. And I'm going to put a box around this. So this is x plus 1 to the third power. That was already something I don't like to do. And so as an exercise here, let's go ahead and do this. We're going to write this as, I was thinking 3, x plus 1 to the third times another x plus 1 here. And what we're going to do is we're going to take all of this that we just did here, x plus 1 to the third, and we're going to substitute that in. So we had x cubed plus 3x squared plus 3x to the first plus 1. All of that times another x plus 1. And this will be the final one that we look at here. We're going to be discussing a pattern if we see any here. So going ahead and distributing our x cubed, looks like we get x to the fourth plus x cubed. And then we'd say distribute the 3x squared, we get plus 3x to the third plus 3x squared. Now we'll distribute our 3x, so we get 3x to the second plus 3x. And then we'll distribute the 1 here, so we get plus x plus 1. And so combining like terms here, we get 1, I'm just going to be clear on that, 1x to the fourth. Now x to the thirds here, looks like we get 4 of those. So we say plus 4x to the third, that's a 3. Plus now, how many x's to the second? Well, we get 6 of those guys. We say plus 4x's to the first plus 1 constant. I'm going to put a big box around this right here. Okay, so in discussion of, do we see any patterns here? Well, first of all, I already recognize that this is undesirable by conventional means, which means multiplying it out the old-fashioned way. So if we could detect any patterns here from result to result, then maybe that would be helpful. And one pattern that I want to point out here is this one right here. And it is referred to as, or remembered as, Pascal's triangle. So I'm going to label this here, Pascal, P-A-S-C-A-L, Pascal's triangle. And when we discuss what Pascal's triangle is, I'm going to go ahead and just tell you this now. Pascal's triangle, this is very important, describes the coefficients in the expansion of some binomial to a power n that is 0 or greater and an integer. So when you look at Pascal's triangle, I'm going to point this out here. We get 1, we get 1 and 1, we get 1, 2, and 1. Before I do anything else, I want you to see this here. We got 1, 1, and 1. Look at our coefficients here, 1, 2, and 1. The next one is coefficients 1, 3, 3, and 1. When we go look at Pascal's triangle, it has 1, 3, 3, and 1. 1, 4, 6, 4, 1. If we go back and look at our pattern here, when we took x plus 1 to the fourth, we got coefficients on our binomial expansion of 1, 4, 6, 4, 1. So just to be clear on this, before we even learn how to remember this, if you already know it, great. But before we even learn it, we're just going to recognize this. What it does is it tells you the coefficients on your expansion here, depending upon what power you're taking this to. And so I'm going to go ahead and write this here. I'm going to write n is 0, n is 1, n is 2, n is 3. Next to my rows over here, n is 4, and n is 5. Where n, we're going to recognize, is the power that we're raising this to. So we're going to write a note here. N is the power on our binomial. when we do a binomial expansion. So if we know the power, we can just go ahead and refer to this triangle here that I'll go through the values on here in just a second, and figure out what would our coefficients have to be. Afterwards, all we have to do is look for a pattern amongst our variables. And so in terms of our variables, let's go ahead and take a quick peek at that. On our first one here, we got 1x, and I'm just going to write this 1x to the 0, really. Draw a little arrow here. And then we say x plus 1. We got 1x to the first plus 1. And then we'd say, in terms of our variables here, you can see x plus 1 to the second. We got x to the second plus 2x to the first plus 1. You can see how these variables are kind of going in descending order as we go from left to right here. So we're going to be able to detect a pattern amongst the variables as well here when we generalize this. But for right now, what we're going to say here is this. Any binomial x plus y to the n, we can find its coefficients by using this triangle. So in terms of what we see about this triangle, what are some patterns? Well, we notice that on the outsides here, there's always a 1 on the outside. So this is always going to be true about Pascal's triangle. And in terms of how we get its entries, basically what's happening is this. We're adding these two previous terms here to get this term below it in between those two terms. So we say 1 plus 1 is 2. If I were to add, the 1 plus the 2 here, I get 3. If I were to add 3 plus 3, I get 6. Or, 4 plus 1, 5. Or 6 plus 4, we get 10. Here also we get 6 plus 4, or 4 plus 6 is 10. So this triangle, you can see how it says etc. goes on forever and ever and ever. So as we get into our binomial theorem in the next one here, that really is just going to be a grand way to generalize, well, hey, if I am taking a binomial to a power that's 3 or higher, how could I more efficiently do it? It's going to utilize Pascal's triangle, and that's what Pascal's triangle represents, the coefficients in a binomial expansion. Cheers.